Hi everyone. So in this video we will have a look at force sensitive resistors, or an FSR for short, specifically the FSR 402, which is manufactured by Interlink Electronics. Now this FSR is similar to a resistive or a strain gauge type and is quite commonly used in applications to find acting forces, pressure, detect the position, or even the presence of an object or event. This can also be used as an input signal for another system or just simply to record data. So in this video we will first run through the basics and the working principles of this sensor, and then have a look at the circuit design and the Arduino code to calculate the force or the pressure. So if you guys like this video, don't forget to give me a thumbs up by clicking the like button below, and if you haven't done so already, please subscribe. I'm Chums and welcome to That's Engineering. Right, so there are multiple types of load cells or FSRs out there. Some of these would include piezoelectric, capacitive, and even hydraulic load cells. So the focus here is mainly on DIY or even research-based projects, keeping industry-level applications aside. So it's really up to you to decide what would be the right type of FSR for your project. But the three main types that I have come across are capacitive, piezoelectric, and resistive, which is what we will be looking at in this video. So these are some of the applications in which you could use various FSRs. In one of my previous projects, I used a FSR to measure the force exerted by an elastic band when restricting a person's muscle. And then I used a simple equation to calculate the pressure from the force. And FSRs are widely used in robotics and automation. They are even used as human-to-machine interfaces and even in various touch-based applications. Right, with that, let's have a quick look at how a FSR works. Now, this is derived from a strain gauge, which is what I've tried to draw here. It consists of a metal foil attached to a body using some form of an adhesive. So when a force is applied, the body undergoes some amount of deformation, which results in a strain, which in turn results in a change in resistance. So this change in resistance can be picked up using a circuit called a Wheatstone bridge. It consists of 4 strain gauges, R1 to R4, an input voltage V in and an output voltage V0. So when a force is applied, there's a change in resistance, which results in a change in V0, which can then be detected. Now, the FSR 402 works on a somewhat similar principle. It's part of the FSR 400 series developed by Interlink Electronics, and I even believe they had a patent for it way back in 1985. So the FSR 402 consists of 3 main layers. The bottom layer is a flexible substrate which is coated with a layer of conductive ink. In the middle there is a plastic spacer, and the top layer houses the electrodes or the active region. The electrodes are somewhat similar to the metal foil on the strain gauge. Now, due to the spacer, there's a tiny gap between the top layer and the bottom layer. So when a force is applied on the active region, the top layer touches the bottom layer and forms a connection, which results in a change in resistance. So the active region touches the conductive ink, which forms a change in resistance. So the relationship here is that the force is inversely proportional to the resistance. So as the force increases, the resistance of the sensor decreases, and vice versa. Now, if you want the exact relationship or the force versus resistance graph, you can find that in the data sheet, and I will leave a link to that in the description down below, so do check it out. One other point that I would like to make is that the electrodes and all these components are kept at a micrometer level. Apart from being the reason for the FSR's flexibility and applicability in small space, One other reason that this is done is to reduce its dependency on temperature so that the readings will be more accurate. Moving on, the main advantage of using any of the FSR 400 series or any resistive type force sensor is that they are cheap and easy to use. They are also flexible and have a very low thickness, so can be easily integrated into tight and small spaces, which is ideal for things like human-machine interfaces or medical devices. However, the main problem with resistive type sensors is that they are significantly affected by electromagnetic radiation and vibrations, which results in quite a lot of sensor noise and interference. If I was to recommend the best type of sensor, it would probably be the capacitive type, for the simple reason that it is a more rugged sensor. It is sealed, so it's not affected by dust or humidity, and it outputs a direct voltage reading. What I mean by this is that the FSR 402 is an analog sensor, which means its output is just a change in resistance. So another circuit is needed to convert that analog signal into a digital signal. In other terms, you need an analog to digital converter. But for a capacitive type sensor, you get a direct voltage reading as the output, so you don't need the extra electronics. However, the main problem with the capacitive type sensor is that it is expensive. So now let's have a quick look at the circuit diagram, and then we will move on to the Arduino code. Right, so now let's get into building the circuit for the FSR 402. The components that we would need are an Arduino, an op-amp or an operational amplifier. Any op-amp would do. I'm using the LM324 IC, a 10 kilo ohm resistor, the FSR 402, and a couple of connecting wires. So in essence, this is the circuit that you would want to implement. The FSR 402 is here. It's connected in series to a 10 kilo ohm resistor, which forms a voltage divider. The output of the voltage divider runs through the op-amp and then into the analog pin A0 of the microcontroller or the Arduino. I've also connected an LED to pin 2, which more or less acts as an identification for when the FSR has been pressed or when a force has been applied. So this LED can be replaced with any component or any circuit that you would want to control using the FSR. The LM324 IC has 4 op-amps in it. I'm using the first one. So the first pin here corresponds to the output of the op-amp. The second pin is the negative pin, and the third pin is the positive pin. The fourth pin is for the output rails of the op-amp, the power rails of the op-amp, which is plus 5 volts from the Arduino, and directly opposite that is ground. So in essence, this circuit has a 5 volt input from the Arduino. That's the FSR. And that's the 10 kilo ohm resistor. So the output is taken actually across the 10 kilo ohm resistor. Now for an analog application, you can directly use this voltage reading. But as we are connecting this to a microcontroller, it's better to have an op-amp. It's not mandatory, but it would be ideal. So the output goes into the positive port of the op-amp, and the negative port connects to the output as such. What this forms is called a unity gain configuration, where the gain of the op-amp is equal to 1. So the input voltage is exactly the same as the output voltage. But because these two voltages are the same, you might wonder, why do we really need an op-amp? Well, for an op-amp, the input has an infinite impedance. And what this means is that the current draw to the input is 0. There is no current draw at the input. On the other hand, the output from the op-amp has a 0 impedance, which means there is no voltage drop across the output. So practically what this does is that it provides a level of isolation between the sensor and the microcontroller, and it prevents any signal attenuation due to mismatching impedances, again between this circuit, the sensor circuit, and the microcontroller. So one last thing I would like to mention is why I chose this resistor here to be 10 kilo ohms. Well, that was directly out of the data sheet. In the data sheet, there's a graph of the output voltage versus the pull down resistor. And the 10 kilo ohm resistor more or less allows the entire range of the FSR 402 sensor to be captured. If I'm not mistaken, it's from about 0.1 to 100 newtons. If I remember correctly, I'm not entirely sure about these values. So there are multiple resistor values that can be used, but the 10 kilo ohm resistor allows you to get more or less the full range of this sensor. Do check the datasheet out. I've left it as a link in the description down below, and feel free to change this resistor based on your requirements. So now that the circuit is done, let's have a look at the Arduino code. I will run through two sets of codes. The first one is simply to turn on the LED when a force is detected on the FSR. So in this scenario, the FSR is being used as an input for another circuit or another system or a component. In the second code, we will look at finding an approximation to the force being applied on the FSR in newtons. So let's go ahead and have a look at the first bit of code. So this is the first Arduino script. The LED was connected to pin 2 and the FSR to pin A0 on the Arduino board. Now this is the output voltage of the FSR after the op amp. Within the loop, analog read was used to read the output voltage from the FSR, and this was assigned to a temporary variable value. So if a force was applied on the FSR, the resistance would decrease, there would be some amount of output voltage, and this variable value would have a value. Therefore, digital write was used to turn the LED on. However, if there was no force being applied on the FSR, it would have a very high resistance and the output voltage would be 0. So in this case, which is inside the else statement, digital write was used to turn the LED off. So it's a very simple code. Let's go ahead and run it and see how it works. So this is the circuit for the first Arduino script. The FSR is connected to the 10 kilo ohm resistor through a voltage divider configuration, the output of which is connected to the LM324 op amp, and the output of that goes to pin A0 on the Arduino. In turn, the LED is connected to pin 2 on the Arduino. So this circuit is pretty straightforward. When a force or an object or event is detected on the FSR as such, the LED turns on, and when there is no force, the LED is off. So like I mentioned earlier, the LED represents any sort of circuit or system that you would want to turn on when an event is detected on the FSR and be off when there is no force on the FSR. Moving on to the next Arduino script, we will try to find an approximation for the force applied on the sensor. But before we do that, there are a few equations to take a look at. So this is the basic circuit diagram that we discussed previously, and this is the resistance versus force graph for the FSR 402 taken from the datasheet. So it's on a logarithmic scale, and you can see that initially for a very small change in force there's a huge drop in resistance, after which only the inversely proportional feature of the graph can be seen. So the resistance of the FSR as per the datasheet varies from about 200 ohms at maximum force to about 10 mega ohms when no force is applied. To calculate the output voltage V0, we can use the voltage divider equation, which is R, the pull down resistor, plus the resistance of the FSR times the input voltage. So there are two cases to look at. The first case is when no force is being applied. When no force is being applied, the resistance of the FSR is at its maximum. So in this case, V out would be equal to, by the way, we're using a 10K pull down resistor. The resistance of the FSR would be 10 mega ohms times the input voltage, which is approximately 0.05 volts, which is in essence 0 volts. The second case is when maximum force is applied. So once the force applied reaches its maximum, the FSR becomes saturated. So if there is a further increase in force, the resistance will not change. So in this case, the output voltage would be found by using 200 ohms, and that would give approximately 4.9 volts, which is almost 5 volts. Right, so when writing the code, we would get an analog value when reading the output voltage into the Arduino, and this would be from 0 to 1023. Now this analog value would have to be converted into a voltage to represent the output voltage, and this can be done using the map function on the Arduino. So it would be from 0 to 5000 millivolts. The output voltage can then be used to find the resistance of the FSR by simply rearranging this equation. From the resistance, we can then calculate the conductance, which is equal to 1 over the resistance. So the conductance can then be used to approximate a value for the force by taking into account this particular graph over here, the resistance versus force graph. So once the force is known, we can then calculate the pressure. Pressure is simply force over area, where the area corresponds to the area of the active region of the FSR, which can be found from the datasheet. Right, so let's have a look at the code. Right, so this is the code for the second Arduino script. Resistance and conductance variables were set as unsigned long, and the variable for force was set as an integer. So within the loop, first the analog read function was used to obtain the analog value from the FSR pin. This was then mapped to produce the voltage or Vout. So 0 was mapped to 0 and 1023 was mapped to 5000 millivolts. An if statement was used to check if the voltage reading was 0. If it was printed on the serial monitor that no force was applied, and it returned to the start of the loop. If, however, there was a voltage reading, this was printed out and then the resistance was calculated. So this equation was derived by rearranging the voltage divider equation. From the resistance, the conductance was calculated. So conductance being 1 over resistance multiplied by 1,000,000 to get it in microohms. Finally, the resistance versus force graph was used to approximate the force based on the conductance reading, and this was then printed out in newtons. So let's go ahead and run this code. Right, so with regards to the demo for the second Arduino script, I have already uploaded this code onto the Arduino. So let's go ahead and open the serial monitor. And you can see that there is currently no force being applied on the FSR. So if I was to touch the FSR lightly with my finger, you get a small force reading depending on the analog reading and the output voltage in millivolts. If I was to press it a little harder, it goes up to 2 newtons, can bring it up to now 4 newtons. And if I let go, it comes back to that no force has been applied. Right, so that's all for this video. If you guys have any questions or clarifications, please feel free to leave a comment and I will do my best to get back to you. If you guys have not done so already, please give me a thumbs up by pressing the like button below, and please don't forget to subscribe. Thank you all for watching. I hope this video helped, and I'll see you in the next video. Cheers.